someone talks about an inverse function, it has two meanings, and that's the problem. Which one do we want? And when you read the college books, you'll see that they show the two meanings. The pre-calc books really don't. So this gets a little confusing. So you're going to have to ask if there's confusion. Um, log is supposed to be a log function. What's that supposed to mean? So we are going to do inverse functions, inverse trig functions, log functions, and their properties. So there's a lot today. Okay, so you should have your handout out. It's yellow. And it says, what is an inverse function? Or inverse of a function? How do you know if two functions are inverses? They undo each other. And even I'll get confused a little bit with this because you just have to think of it carefully. So if I have f of x, and then I have f inverse of x, those are two different functions. And if we undo, I'll write it out. I'm going to use my notes so I don't miss something. Function, and this is the inverse function. You can talk about inverse operations. That's a different thing. Interesting, because that's on my notes from last year. They undo each other. How can we write that symbolically? Remember, you have to do f of, do you remember this? F inverse. Now, if these functions really undo each other, when you put x in, this will do something to it, and then f will undo that, and so what should you get back out? X. And you have to go both directions. You have to do f inverse of f of x. That's also going to be x. So you must check it both ways. Okay? So we can sometimes have double meanings here. This is where the problem is, especially when we do derivatives of inverse functions. It's really complicated. Okay. You also remember that an inverse is a reflection over what? An inverse function. Look, forgot the word over. Reflection. Reflection over y equals x. Yeah, you guys are not supposed to have especially oranges. They're nice. Okay, so let's graph y equals x squared. So at least get somewhat reasonable. You know, the other side's exactly the same. Okay, Eric? So there's my function. And then it says, what is x if the y value is 9? Well, there's two values. 9 is equal to x squared. What's x equal to? 3 and negative 3. Is the square root of 9 negative 3? If you solve that, I could get the 9 on the other side and factor, or I could square root it. And I get real particular about this. What is the square root of 9? It's 3. No, it's 3. What is the square root of x squared? Absolute value of x. Because x could be a negative number. For instance, if you were to ask to do this, you can't say it's x, because what's x here? Negative 3. Square roots, we choose to be positive. Why? Because when I take this function here and try to reflect over, I'm going to have to trace it out a little bit. So when I try to reflect over y equals x, I'm not directing this very well. And then we can graph y equals x. I've got a problem. Try that one. There's y equals x. Now I'm going to take this, and I'm going to move it. And I didn't want to do that. one more that I meant to move it. Maybe if I locked this down, I'd be in better luck. I just want the green thing. There we go. And I'm going to rotate it. Okay, there's my reflection over y equals x. What is the problem with that? It's not a function. How do you know it's not a function? That's the vertical line test, right? So what we do is we restrict, and I'll do it in purple, I guess. We restrict our domain to either be the x greater than 0, which is what we've always do, and then I only get the top half of my square root function. Because the inverse of this is not a function. It's not to say it's not an inverse, but it's not a function. So you got to be careful with that. Okay. What is true about our domain of our original function? Do you remember this about inverses? F of x. Okay, the domain here is x belongs to the reals. And what's the range? 0 to infinity. Do I get to include 0? Yes. Okay. I'd rather write it this way. Y is greater than or equal to 0. Now, what about the inverse function? You remember that? Because this is how I'm going to do the logs. Because I always get confused on logs. What's the domain for the inverse here? It's the y value. So x is greater than or equal to 0. And what happens to the range now? The y is everything. We have to restrict it. Because you don't want an inverse that's not a function. Because then it doesn't behave like a function. You can't talk about continuity. You can do derivatives, but it's tricky. So restrict the domain so that x is greater than or equal to 0. So when I do that, what happens to my range here? Then my range is going to be, if x is greater than 0, y is still positive. So x is still positive, but what happens here? If I make this x greater than or equal to 0, then this will be y is greater than or equal to 0. So we just fixed the problem, that's all. Okay, ready? Now, do you know what a one-to-one function is? Now, by the way, we write it this way. One-to-one. That's all. Math people are lazy, so we invent things like that. So for every input, there's exactly one output, and for every output, there's exactly one input. For every input, when they say exactly, that means it has to exist. It can't be any more than one. Yes, it will pass the horizontal line test. Exactly one output. So for every input, there has to be an output. So for every student in here, there has to be a desk. This is not a one-to-one function or chair. For every chair in here, there has to be a student. I see some empty chairs. It's not one-to-one. So for every output, there is exactly one input. Grant has already asked the question, how do you know if it's a one-to-one function? You have the horizontal line test. That doesn't pass it. This should be all review. But it's kind of theoretical, so it gets to be a little confusing. We kind of did this next example. We'll do it again. Okay, ready? We're saying parabolas on here. Now, I didn't have a function in it, where it's any function. Let's do an exponential function. So just take any old function. I want to have an inverse. Kind of. It's a little more flatter than that. E to the x grows faster. And you know what? They're not going to give you 2 to the x. They're going to give you e to the x. Because the derivative is a lot easier. You might have some with 2 to the x. Now I'm going to actually draw this because I think I'll do a better job drawing it. Now this is at 0, 1. With x and y switch, this is going to be at 1, 0. It's not too bad. So if you get confused, draw the function and reflect over y equals x. Right. We're going to talk about logs in particular. So just think of this as f of x, and this is f inverse of x. Question? Okay. Maybe I'll bring up my calculator. I think I have it up. What about the sine of x? Okay, now remember, we have to restrict the domain. You know what the sine of x looks like, right? It looks like this. Is its inverse a function? No. So we're going to restrict the domain. Now, this is the problem with doing inverse sine. Okay, so now, if I solve for x in terms of y, I'm inverting it, but it's not a new function. So what is x equal to? Inverse sine of y. What is x, though? X is what? Physically here, geometrically here. This is the angle. So if you can remember that an inverse sine is nothing more than an angle. So this would be like saying 1/2 is equal to the sine of 30 degrees. So when I put it in here, inverse sine, I always change it back to that. But anyway, this is going to be the 30 degrees. And this is going to be the 1/2. Now that's all in the same function. So this is 1/2 right here. That is not the inverse function. To get the inverse function, we switch x and y. So we have y equals sine of x. This now will be a new function. We say x equals sine of y. Solving for y, we get y equals inverse sine of x. How are we going to restrict that? Right. So on this one, my y is going to be an angle. So y is going to be between pi over 2 and negative pi over 2. Okay? Or the x is going to be. I'm looking at this new function. Yeah, it's different. That's why you get confused too. No, this is the inverse function. Do you remember what it looks like? Now, I think I calculator, I have it on. I do. So let's add a graph. And my smart view doesn't work, so it doesn't really matter. So I'm going to go y equals the sine of x. Well, it depends on how you're doing it. If we're talking about the new function, these are angles, and these are numbers. What is this y value going to be between? 1 and negative 1. And we want to keep ourselves between negative pi over 2 and pi over 2 because that's now a 1-to-1 function. Shall we go ahead and graph the inverse? It should come out nice. I might want to erase that. Now, where is that? That's in my trig. There it is, inverse sine. I like to cheat. This is a new function. And I'm going to erase the green. I like the fact that they fixed that. There it is. Now, can I make this a little bit bigger? Come on, let me grab the axes. No. No. Oh. I know it's not letting me grab the axes. Sorry. But there it is. Okay? So you're going to have to remember that when your calculator spits this out, it's going to spit out a value between minus pi over 2 and pi over 2. That's going to be the problem. Some of you are going to want to go into another quadrant. Then you have to do some work. And actually, if I were to continue this and not have a function, it would look something like this. Something. Not great. But the Inspire, I think, does a nicer job with the actual graph. So now we get a pretty picture of it. Okay, I'll put it so you can see it. Okay, do you remember how to find the inverse of a function? Now, on the college books, they tell you to solve for x in terms of y and then switch, but we're going to switch because it's much easier. Switch x and y, and then solve for y. You really need to do the practice problems because sometimes it's tricky. Whoops. How do you graph? You reflect over y equals x. So if I gave you y equals x plus 4 over x minus 4, and I want the inverse function of that, what's cool is the CAS calculator will actually do it for you. Yours won't. What do you have to do? You have to switch x and y. So I'm going to have x. Let me erase that. This way. Okay. So if x equals y plus 4 over y minus 4, this is why you need to practice. Do you remember how to solve for y? Well, math always tells me what to do. I have a proportion. Somebody said it. Cross multiply. I can't think of anything else. I'm going to get x times y minus 4x. Remember this last year? And this is y plus 4. And I want to solve for y. What I do is I circle the y's. And those are what I want to get together because that's what I want to solve for. So the y's are on opposite sides. Now, can you do this as quickly as I can? I'm going to put this y over there and then minus 4x over there. You can show all the steps if you'd like, but you're now in calculus. I think you can do this. It's x times y minus y, right, equals 4 plus 4x, or 4 plus 4. Now the question is, what do you do here? Oh, you guys remember. Good. You factor y, so it's y times x minus 1 equals 4 plus 4x. Now, the CAS calculator will do it for you. It's kind of nice. So if you're on the SAT and they ask for an inverse function, you are allowed the CAS calculator, you can do that. You would have to practice. Not the ACT, the SAT. I think that's going to change sometime in the future. It hasn't changed yet. You can use it on the AP test. Now, the AP test, now be careful, because the AP test is written so that no student has an advantage over another student. So, if you use your CAS calculator and don't show your work on something where the calculator is allowed, you will not get the points. I know, because I graded a problem like that. I disagree with it because it was something that you could have done in your head, but anyway, I didn't win. So last year, the CAS calculator was actually disadvantaged. Last year, the CAS calculator was actually disadvantaged because the kids who had the CAS calculators approached the problem not in the easiest way. They were going to use the calculator instead of thinking there were easier ways to do it. I can't remember the problem off the top of my head. If I remember, I can bring it in. Okay, that's all you have to do. Now, we're going to fill it in. Now, notice what's true. This is 1-to-1. This is 1-to-1. This is not 1-to-1. This is 1-to-1. This is 1-to-1. Also, I'm kind of out of space here. This is 1-to-1. What's special about these two cases? They're what? How does this differ from this one? This one's what? In. What about this one? This one decreases and then increases. So the way you get one-to-one functions, they have to always increase. I think it's always increasing if Bill said this correctly. Or always decreasing. Or in question, you're supposed to be taking notes. Okay? Does that make sense? The function's either always got to be going up or always going down. You can't have a mixture of increasing and decreasing. So this is decreasing here and then increasing. Okay, that's just about inverses. We are going to deal with the logarithms. We'll do the, I think that's, no, I don't know how much in there is about the trig. Now on Monday, we are going to do the parametrics. Make sure you bring your calculator on Monday for sure. You'll see that on, no, this is a BC topic. Huge. It's always one free response question on the exam. Okay, so you've got to know the parametrics. We're going to start that on Monday, so you need to bring your calculator. There's only two full BC problems, and one is a mixture. Yep, it's exactly similar to that. Okay, let's do the logarithms. Okay? Ready? Question. Yeah. Increasing and decreasing. Usually you have time to work. You probably have some time to work. But if you look through this handout, there's a lot of problems to practice with. We may do some and may leave them for you to do. But this is a really good review of logarithms. Okay? I think I got 2 pages there. And then you have questions on homework. Okay, Eric, ready? If I graph this, y equals a to the x, where a is any base. Now keep that straight from, this is an exponential. Keep that straight from this. That's a power. Let me just give you a quick example. 2 to the x versus x squared. This is a polynomial. Polynomials behave nicely. Actually, exponentials behave nicely, but not at all in the same way. We're going to do a ton of things with powers. We're actually going to take a exponential function and approximate it with a power function. And you may be saying, how do you do that? Well, that's what the second quarter is. The whole quarter. Yeah, it's not that hard. It's just very new. So you'll find it hard. Okay. You see the difference between an exponential, 2 to the x, and a power, x squared. Because you might both think they're both powers. That's not true. Okay, so we're going to graph y equals x here. And then we're going to graph our inverse. That's not too bad. By the way, what point does this go through? If it's an exponential, I don't care what the base is. It's 0, 1. Then this is 1, 0. So later on this year, we're going to have to worry about derivatives of these inverse functions. You remember that was tricky last year. Okay. This way? Usually it's the bottom. Okay. What's the domain? You should be able to write this out. What's the domain for my exponential? 0 to infinity. Lauren, what's the range? Is that true? 0 to infinity? Can't you have negatives? This is the exponential. Of the exponential is what? Minus infinity to infinity. That's 0 to infinity. Now, on the logarithm, I'll change colors. So we're color coordinated. What's the domain for the logarithms? 0 to infinity, and the range is? Okay, when they ask you this on the exam, they might ask you for the domain of some sort of logarithm. Like if I have the log of x minus 2, You get the point for the first statement. Okay, well, how am I going to find the domain of that? What is domain? Input. Could be x's, could be t's. So your input to this function, I don't care what is in there, it's a composite function, x minus 2 must be greater than 0, so what's true about x? It has to be greater than 2. You get the point for this line right there, even if you can't solve. Which is nice. Nice you get that point. Because what has to be true about the input for your logarithm? No, I didn't. Oh, I made up the function. Yeah. Just make it up otherwise. Okay. So now exponentials, we can kind of get that. That's not a problem. You're taking 2 to some power. 2 to the first, 2 to the second, 2 to the third, whatever you want to do with that. What if I want to undo it? Now remember, think back a long time ago. Before they had logarithms, Napier's the one that discovered or invented them. Invent might be a better word. But if I wanted to find out the x value to make that true, Grant, I need you to, if you're not going to pay attention, that's fine. What value works there? 3. Because what did you do? You did trial and error. What if my y value is 16? Okay, now you're thinking, this is why I like the calculators, because the calculators, before you had to do all this crazy stuff called interpolation to find out what happens when y is 10, now we can actually think about understanding. If 8 gives you an answer of 3 and 16 gives you an answer of 4, 10 is clearly between 8 and 16. So what will be true about my x? It'll be between 3 and 4. So it gives you a better feel for what it is. It's a decimal besides, which, how do you even operate with that? So Napier invented a way to undo it and find the inverse operation. So he said, well, x is equal to, uh, 2 to the y. So how do you solve for y? That was the problem. I would have preferred to call it an inverse exponential, but he didn't. He said it's a log. So to solve for y, he made up his own operation. Same with square rooting. Squaring probably came first, and then some. Why do you use this symbol? Because somebody told you that's what that symbol meant. So when you look at a logarithm, it's asking for the exponent. So that's what I think is crazy. I mean, it's a crazy word, but it's log base 2 of x. And when I look at this, I have to go back here. What does this mean? 2 to the y is equal to x. That's how I do it. I don't ever think in terms of logarithms because you're looking for exponents. And I'm not really quite sure what they do. So we always go back to the exponential because we understand that. Now, here's the other thing, and I can't bring up my calculator, unfortunately, because it doesn't work in here. If you were to take this now, and you can think of it 2 ways, you could just log both sides, and using properties of logs, what base would you use? Base 2. That's an operation. It undoes the exponential. Okay, well, you got to be careful here, you guys. Only if you have the new operating system on a TI-84 can you just type that in. TI-83 will not do it. You don't have that option. It's only base 10. Right. On the 84, you don't need the change of base. There's a button, which is nice. However, to take the derivative of this stuff, I have to do a change of base to figure it out. So do you remember how to do that? No. What are the only bases we have? What are the only bases we have? Base E and base 10. So I could write this log base E of this number, which is 10, over log base E of 2. Well, we don't write log base E, do we? We write what? ln. So it's the natural log of 10 over the natural log of 2. And remember our derivative of e to the x? What's the derivative of e to the x? It's e to the x, like a phoenix rising out of the ashes. Yes, we'll be reviewing all that. I'll get all my signs up. I haven't gotten there yet. Okay, guys, can you divide 10 and 2? Okay, can you divide 10 and 2? No, it's not in our properties of logs. You can't undistribute these things. That's what you're trying to do. Now, if I wanted to do base 10 log, it's log base 10 of 10 over log base 10 of 2. Does anybody know what log base 10 of 10 is? 1. They're undoing each other. So it's 1 over log base 10 of 2. Now, we don't write the 10. Could have picked 11. That would have been a little nicer, because then it would look similar to that. It's either going to be LOG or LN. Now, if you have an 84, there's a button on the calculator. So that's kind of nice. Okay, so let's look at our properties of logs. Remember them? If these bases, can you see this okay? If these bases match, this is 1. Now, if you don't know what that is, here's how I do it. Okay, guys? Let's say you don't know what it is. Call it x. Then I go a to the x is equal to a to the first. What's x? 1. So if you forget, just undo it. So log base a of 1 is equal to x, which means a to the x is equal to 1. What's the only value for x? 0. The other thing to do is to think of inverses. Anybody know what 3 is going to be? It's just x. Because I haven't done this one, let's do 9. This is r times log base b of x. Don't forget. Oh, I'm sorry. I didn't realize I was on the other side. Well, we have to. We can write it right on the front side. But do you remember that you can bring the exponent out in front? Do you remember that? You want to remember that, because when you do derivatives, you're going to want to simplify your logs if you can. Pardon? Oh, we're going to go through them all yet. But this one, see, I can say is equal to this. This now, knowing that one is x times log base a of a. But we already know that this is 1. So this is just equal to x. Okay, you ready? Do you remember the log of a product? 4. Oh, I'm sorry, I missed 4. What's 4? That's a base a here. That's just x. Okay, 5 is log of a plus log of b. What about 6? Can you distribute that? There will be at least one person in here that will try it. If you could distribute it, I'm going to put it in red, it would look like log of a. I'm going to teach you how to think through some of these things. Log of b. Are these sides the same? Yes. Are these sides the same? No. 8 log of a times b is, well, it will be. No, it won't even. I can't even think of a number that'll work. So guess what? Can't do that. Yeah, I was thinking about that, 2 and 2. It's the only time it works, but that other rest of the time, no. So you can't, this one can't be done. You just have to leave it. But a lot of people want to change them. Okay, what about this one? Okay. No, let's do that color. This is equal to the log of a minus the log of b. Using the same kind of thinking that I did on 6, what about that one? You could do a change of base, but that's it. Just leave this alone. Can't hear you. What's the question? Somebody asked me something. I just couldn't hear. Pardon? What's a natural logarithm? It's a log base what? E. What's the natural log of E? Because this is base E, right? What's the natural log of 1? 0. Okay, so you have to remember these things. I think we only have one day on this, I'm pretty sure. Okay? Can I change pages now? There's some nice little problems. Now, I don't want to have all these exponents. Let's do that one. Okay, first, we have a log of a product and a division problem. So, Eric, how am I going to do this? It's the log of x cubed times x minus 3, but it's divided by y. Just like that? The natural log of a divided by b is equal to the natural log of a minus the natural log of b. I wish we could fix that. Okay? I just heard y. Maybe I heard wrong. Okay, what about this one? Can I do this one still? The log of x cubed plus the log of x minus 3 minus the log of y. I'm not going to say natural log because it's all we ever work with anyway. One more thing. Yeah. Plus the natural log of x minus 3 minus the log of y. That was it. I remember when you guys did it in pre-calculus, you struggled with it. Is there something? I think I had something there. I don't know if it's on yours. Yes. You should be doing notes. Okay. You can draw outside of class. How about number 7? Right is a single log. Can you do that one? Number 7. Then I'm going to let you have some time to work with these, unless you want me to do them. This is the log of the square root of this. Now, one of the questions that arises, well, wait a minute, is what is the domain? You have to go to the original problem. You do have to worry about that. You can't look at the final answer because it might simplify to something where the domain is bigger than what it really is. You have to look at the original problem. Well, this is the same as this. Don't throw, please. Yeah, we don't throw. Hey, guys. Trevor, how do I do with that one now? How do I do this? X squared minus 1 over x plus 1. You have it on your sheet. So I could do this if you want me to. X squared minus 1 over x plus 1 to the 1 half. And I can put the 1 half in front. So that's 1 half. That's true. X squared minus 1 over x plus 1. And can you now reduce that? Yes. But in the reducing process, you are changing your domain. The domain for this final one will be different than, maybe different than the first one. It may not be, I don't know. I'm just saying you have to go to the original problem to find the domain. This is what? X plus 1, x minus 1 over x plus 1. And what happens to x plus 1? So it's 1 half log of x minus 1, provided that x is not equal to negative 1. So I simplified that, but there are other issues on the domain. This part right here, how would you solve that? What's got to be true about what's inside of here? Or actually, the whole thing. What's true about the square root of x squared minus 1? It's got to be greater than 0. Well, square roots are always greater than 0, so I don't have to worry about that. Right? Square both sides, so x squared minus 1 is greater than 0. I saw this on the BC exam this last year, something similar to it. Students had a tough time with it. We are never going to have imaginary numbers in this class. But I saw imaginary numbers on the exam because it was similar to this. Not in calc, not even in pre-calc. Okay, higher algebra. How do we solve that? That's a quadratic inequality. Do you remember? test line, except I need the test points. So I'm going to factor it. You could say x squared is greater than 1. I think this is safer because you don't really know what to do with that absolute value. So where are the test points? Negative 1 and 1. And now we are solving. So we are looking for any numbers that make that true. You can just substitute them in, but I also know that that would be a parabola, like this, right? So it's positive, negative, positive. So this domain is from negative infinity to negative 1 and from 1 to infinity. If I go over here now, guys, don't do that. If I go over here, what's true about this? What has to be true about x minus 1? X minus 1 must be greater than 0, so x is greater than 1. Well, guess what? I lost this piece right here. So you always have to go back to the original function to find the domain. And yes, they ask these questions on the exam. AB and BC. This is an AB topic. That's why we review all the AB, because 60% of the exam is AB. So we want you to do really well. And we did. I think we averaged 4.5, I think, on the AB this year. Out of all the 670 kids. And we averaged 4, I think, out of 5 on the BC. Good. Those are good results. Okay. If you just even pay attention in class, that works. So do you want to do these problems on your own? Or do you want me to do them? You can do them, or you can put answers up. I don't have any answers. Well, maybe. Ellen? Oh, are there questions out of homework? And I also want to get your homework quizzes back. Now, how we're going to do the homework quizzes is you can correct them. You have to correct everything. Well, it's a homework quiz. Oh, my goodness. We don't have time for me to do them. I'll give you back your homework quizzes. You have to correct them, and you can get half points back.